Hello. You may be curious how in your math books over the years, they've had formulas written in there, like the volume of a sphere as 4/3 pi r cubed, or the volume of a cone is 1/3 pi r squared times h. We're actually going to use volumes of rotation now to generate some of those formulas. You're going to do some of the easier ones on your own, but I'm going to do one of the harder ones in this video. Okay, so let's start thinking about the volume of a cone. So if I were to draw a region like this, that's a triangle. I could rotate it over the x-axis, and in the rotation, I could form a nice little cone there. Now I could specifically find a cone that had a vertex here. Let's say this is at 4, 0, and this point right up here is at the point 0, 2, and that's going to be the origin down there. If I rotate that specified triangle, I would be able to find the volume of that specific cone. But if I wanted to do this for all cones, instead of using 0, 2, I could say that that point right there was the point 0, r. So it would work for any radius. And instead of using 4, 0, I could put in that this is the height of the cone, 0. So it's a cone on its side. And then I would be able to get the volume of the cone. Likewise, I could do a similar thing if I wanted to do a sphere. It would be easiest if we center that sphere right here on the origin. And here's a circle, but if I rotate the sphere, the top half around the x-axis, it will form a sphere. We could just work with the first quadrant of this. This would be the point 0, r in general, and this would be the point r0 in general. And we could work with this equation. We know that x squared plus y squared is equal to r squared. And we could then solve and get that y is equal to the square root of r squared minus x squared. This would be true for the entire top half of the circle, since we would only need to rotate the first quarter of the circle around, and then we could double it to get the volume of the sphere. We could just go from 0 out to r when we integrate that. But I'm going to work with an example now that's more complicated than this. We're going to take an ellipsoid, and we're going to rotate the ellipsoid over the x-axis. So let me start by drawing an ellipse. Let me do a little bit better than that. So let me draw it in quarters here. It's a little bit easier. So our ellipse looks something like that. I'm sure you can do better on graph paper, but we'll settle for that. If we remember about ellipses, this point up here would be the point 0b, and this point down here would be the point 0, negative b. This would be the point over here that's a0, and this is the point negative a0. So the distance from negative a to a, you may recall, was the major axis, and from negative b up to b is called the minor axis. We can write that the equation of this ellipse is x squared over a squared plus y squared over b squared equals 1. Now, just like for solving for the sphere, we will need to solve for y if we want to be able to take rectangles in this first quadrant here and rotate them around to form discs. We're going to need to know the equation of this line in terms of y as a function of x. So we need to do a little bit of algebra here. The easiest thing is to first multiply everything by a squared times b squared. So that would leave b squared x squared plus a squared times y squared is equal to a squared b squared, right? The next thing we would want to do is move the first term on the left over to the right. So that would leave a squared times y squared is equal to a squared b squared minus b squared times x squared. All right, and then we can see, looking at that, we have a factor of b squared in both terms on the left. So this becomes a squared y squared is equal to b squared times a squared minus x squared. Finally, we can get that y squared is equal to b squared over a squared times a squared minus x squared. Therefore, y in the first quadrant, we'll just do the positive root, is b over a times the square root of a squared minus x squared. Now, coming back over to our ellipsoid here, if I want to integrate this thing, I am going to use disks. And we know that our formula for disk is that delta v is equal to pi r squared. In this case, since it's vertical, that would be delta x. So in order to keep going with that, adjust something here. In order to keep going with that, we need to solve for r. So what is little r? It's going to be the top of the rectangle, which is right here, minus the bottom, which is at 0. So the top of the rectangle is given by the equation we just determined for y. So it is at b over a times the square root of a squared minus x squared. We're going to want to use r squared. So r squared would be b squared over a squared times the quantity a squared minus x squared. We're going to put that in, and we'll have that the volume element is equal to pi b squared over a squared times the quantity a squared minus x squared. Continuing along, we can turn that into a volume integral, and the volume integral will be, we'll bring those constants out. B and A, while we don't know what the numbers are, those are constants. So we will integrate a squared minus x squared is the integrand. We're going to integrate with respect to x. Oh, and I did leave off a delta x up here in order to have the volume element. So the delta x will become the dx. Now we need to figure out our limits of integration. We said it's easiest to just look at the first quadrant. And so x started at 0 and will end at a value of a. So we're going to integrate from 0 to a. Now we just need to do the mechanics of this. All right. So before I do that, let me remind you that a and b and a right here and the a right here, they're all constant values. Okay. So we don't know what the number is, but we will treat it like any other number. So b could be the number 2, a could be the number 3. We'll treat it just like that as we do the integration. So let's go ahead and do the integration. So this is the volume. Maybe I should call this the half volume because we're only doing the right half here. So I'll call that the half volume would be given by pi b squared over a squared. Now we're going to get the antiderivative of the integrand. Since a squared is a constant, its antiderivative is just the constant a squared times x minus, and then using the power rule for anti-differentiating, x squared has an antiderivative of x cubed over 3, and we'll evaluate those at x equals 0 and a, and use the fundamental theorem. So just subbing back in, pi b squared over a squared. Now let's put in our limits. So when we put a in for x, this the first time, we will get that the first term is a cubed, and the second term is a cubed over 3. When we sub 0 in for x, we will just get 0 for both terms. So let me just write minus 0. Now, it's easy to see that the second term, that the inside of the brackets, the first parenthetical quantity would just be 2/3 of a cubed. and obviously 0 is just 0. Now we can rewrite that. Let's just multiply through. We're going to have in the numerator, a factor of 2. We're going to have a factor of pi. We're going to have a factor of b squared. And then if we look at the a cubed and the a, that will give us an overall factor of one factor of a in the numerator. And that leaves a 3 in the denominator. So there we've calculated what the volume for half of the ellipsoid would be. So if we want the volume for the full ellipsoid, we'll simply double that and we'll have 4 pi b squared a over 3. Now let's check if this actually makes sense. If a equals b, this would be, that would mean we have a sphere. Okay, so if a equals b, we could put in that the volume is equal to 4 pi, we'll just put a in for b, so we'll get an a cubed over 3. Now note, if this had been, if a equals b, this is really the radius. And so we're back to our formula, 4/3 pi r cubed, which is exactly what we would expect for a sphere. So it appears that we do have the right formula for this case. So this case is harder than what you'll have to do for the sphere or for the cone. So this is a good template that you can use when doing those things.